Okay, so we've got a couple more examples to look at with single displacement. Now, single displacement, as I mentioned last time, has this sort of generic formula of taking a single element. That's why it's easy to recognize. We're going to deal with metals. In the lab, we're going to look at halogens, but we're going to look at metals in the lecture class. And then I've got a couple examples here to get you ready for lab. But anyway, you got a metal, element, neutral, no charge, solid form. So this would be like taking zinc metal, copper metal, something like that. And you put that metal into a solution containing an ionic compound. What you're testing here is the metal A with the cation B. Those are what we're basically trying to see is which one, A or B, prefers to hold on to the electrons. So at this point, initially, A has the electrons, B has lost the electrons because it's the cation. And based on what are called reduction potentials, which you study a lot more in Chem 2, if B prefers to hold on to the electrons compared to A, that means it is less active. And the less active element prefers to be alone, which means that the two metals are going to switch places. So if B is less active, and we're going to have our activity series to tell us that, then A and B are going to switch. B is going to become the neutral. It's going to steal the electrons from A. A is going to become the cation and go into solution with C. So it'll be dissolved in the water. Now, if A is the less active metal, it prefers to be by itself, which it already is, so no reaction will occur. So of all the equation types that we're learning in this chapter, this is the only possible scenario where you might just put NR, no reaction. We did talk about with double displacement, if you end up with both products being aqueous, that is just a physical change, so no chemical reaction there as well. But honestly, with double displacement, I usually give you one precipitate, so you have a chemical change. But this is one, we're not doing that today. This is one where the A and B may not react. It may just stay as is. So if you look at your activity series of metals, if for some reason on the test you get it backwards or you start to get confused about what it means, it makes sense that you've got platinum, gold, silver, copper. These are metals that love to be metals, right? That's why we wear them as jewelry, right? Platinum, gold, silver, because when we wash our hands, it's not going to deteriorate, right? They're going to stay metals. So clearly they like to hold on to the electrons. They are very unactive. Metals on the left side, we never find these as elements. They are so reactive that they have to actually be stored in oil because the little bit of water in the air can actually start a chemical reaction kind of spontaneously. And as that reaction starts to occur, it's very exothermic. It generates heat, what makes it go even more. Anyway, the hydrogen gas that's produced is flammable. A lot of times it leads to a fire. These are kind of fun to put in water. But anyway, the metals on the right, copper, and I should say the right of hydrogen, copper, silver, gold, platinum, they are not going to react in water or acid. Anything to the left is. So that's why lead is a really poor choice for plumbing, because over time, especially if that water is slightly acidic, the lead will turn into lead cation, Pb+2, and that turns out to be very, very, very bad for developing brains. It can really pretty direly affect your IQ and mental capacity later in life. So lead is a huge problem if it's in the water supply. Okay, so where we left off, next reaction we have here is we've got iron solid reacting with a copper 2 sulfate solution. So I always thought these were easy to recognize as single displacement, right? They don't look like double because you got to have a compound and a compound. This is just a single element. It's not combustion, it's not acid base. So it's kind of easy. This is going to be single displacement, and also called single replacement. I should say that too. In order for us to answer this question, just know that you've got to go look at the activity series. So this, along with your solubility rules, remember this is going to be given on the test. So you do not have to memorize the activity series. Now, all my handwriting on here, that will not be on there. It'll be blank. But anyway, you've got the iron here, and you've got copper here. And what we can tell is iron is more active, copper's more to the right, so copper is less active. So when I compare the two, copper is less active, iron is more active. And what I did to help myself remember this, because I thought it made it nice and easy, is that the less active doesn't want to play. It wants to be by itself. Okay, whatever helps, right? So what'll happen here is the copper is going to end up alone as the neutral solid. So copper started out as a cation. Since sulfate is -2, the copper here is a +2. And if a reaction occurs, the cation becomes the neutral. Like we talked about on Tuesday, that shows reduction because the charge is going down, it's being reduced. So this is the reduction step here. Copper is taking in 2 electrons in order for it to go from +2 down to a 0. And that means that by default, the iron must be what's going to be oxidized. Now, the sulfate is just here for the ride. It's basically a spectator ion. It really doesn't do anything in this reaction. It's just there as a charge balance ion. Now, the question is, if I go to put iron with sulfate, you'd go to your periodic table and you'd say, okay, obviously this is an ionic compound. I got to balance my charges. I know sulfate's -2, but then you go and you look and you're like, well, wait a minute. I don't know what charge iron's going to be. It could be a +2, it could be a +3, and you wouldn't even necessarily know that as being the 2 most common oxidation states for iron. So you'd have to have a little extra information here. So if we were doing this on the test or quiz or something like that, I would have to tell you that iron becomes the +3 cation. All right. That would be the only way for you to really know what to predict on the product side. So if iron becomes +3 and sulfate becomes a -2, if I crisscross those, right, I would have to have 2 irons and 3 sulfates to get a +6, -6, respectively. This is, oh, well, I mean, technically it could be a precipitate. It's just very unlikely because usually what would form a precipitate would start out as a precipitate. So it's unlikely to have it as a precipitate on the product side. But anyway, check your solubility rules because ionic compounds, we're always questioning whether or not they're soluble or not in water. And just to review that really quick, because the rule for sulfate is sulfates are typically soluble. The exception would be those alkaline earth metals, silver and lead. Of course, iron is not one of those, so it's going to be aqueous. Now, what's going on here, the reason why this isn't balanced is if we really dive kind of deep into the electrons, the iron is increasing its charge, becoming more positive. So this shows the oxidation step. Charge is going up because electrons are being released, negative electrons are being let go. And the iron starts out as neutral and goes to a +3. So that means 3 electrons are being lost per iron. But remember, copper is only taking in 2. So really, the focus of balancing a redox reaction, which you do a lot of in Chem 2, is the balance of the electron exchange, because electrons can't just come out of nowhere and go to some mystery place, right? We have to be able to see where they're coming from, where they're going. Now, the good news is that in Chem 1, we really don't have to dissect the number of electrons. So we don't have to track that this is gaining 2, the iron is losing 3. All we had to do was, if we know iron becomes +3 and we know sulfate's -2, we can come up with the correct compound for the iron 3 sulfate. Then we're just going to use this to balance because I needed 2 irons to make iron 3 sulfate come together. On the reactant side, I need to make sure that I've got 2 irons. I also needed 3 sulfates to make that iron 3 sulfate come together. So on the reactant side, there's only 1 sulfate group. So I multiply the CuSO4 by 3. And then when I do that, that also gives me 3 coppers. So I put a 3 in front of the Cu. All right. Now, the next equation, we have Pb, lead, and we're basically putting it into salt water, NaCl. Now, in this one, we're looking at the lead and the sodium. Again, the chlorine is just a spectator. When I look at my activity series, sodium is a highly active metal. Lead is much less. So lead is a less active metal. Sodium is more active. We remember that the less active wants to be alone, which it is. So this would be one of those scenarios where nothing happens. Technically, yes, over a long period of time, the lead might react with the water that's present, but that's not what this reaction equation is asking us. It's just asking us to compare the lead and the sodium. So the reaction there is not going to happen because lead is less active and wants to be by itself. So in all 3 of these examples, we were comparing 2 metals, or a metal and hydrogen. And hydrogen, again, is on the activity series. So hydrogen is just an interesting nonmetal because unlike the rest of them, it does have positive cations, right? Whereas oxygen, nitrogen, phosphorus, they're always negative. So that's why hydrogen's special. Now, as I mentioned, we're going to be looking at single displacement reactions in lab, but we're going to be looking at the halogens. So we're just looking at the fluorine, chlorine, bromine, and iodine. And it's going to be very similar. You're going to have one of the halogens, in this case, the sodium fluoride reacting with I2. The I2 here, element by itself, in this case, diatomic, because remember, these are part of Hofbrinkel. So like lead is just Pb, we don't put Pb2. But for fluorine, chlorine, bromine, and iodine, when they're in their neutral form, their element neutral form, we have to report them as diatomic. All right, so the I2, right, has no charge. This is going to be the neutral. And then the sodium fluoride, in this case, we're back to thinking about the anion of the halogens, where fluoride is -1, chloride's -1, bromide's -1, and Ia is -1, right? There's no subscript of 2 now because they're ions, not neutral. So the sodium fluoride, we've got the fluorine or fluoride here as the anion. So like we were doing with the metals, if a reaction occurs, the neutral becomes the cation and the cation becomes the neutral. In this case, the only difference is if a reaction occurs, the anion would become the neutral would become the anion. In this case, though, no reaction occurs. And what happens here is because fluorine, if you remember from intro chem, is our most electronegative element, meaning it has great electron affinity or attraction for electrons, much stronger pull for electron than chlorine, bromine, and iodine. So fluorine prefers to be the anion. So fluorine prefers to be the negative, and that's why no reaction will occur when I'm looking at comparing fluorine and iodine. If I switch it though, and I have the iodide and I've got the neutral fluorine, again, fluorine prefers to be the F negative. So fluorine is going to become fluoride and the iodide becomes the iodine. So the anion here, iodine or iodide technically, becomes the neutral. And the neutral, the fluorine, becomes the anion, the fluoride. So there is still redox going on here. What's happening is the fluorine prefers to be reduced. It goes from 0 to a -1. So the F2 is reduced. And if we remember some terminology for redox reactions, the element that is reduced is the oxidizing agent, right? It is what allows the iodine to be oxidized and release its electrons. So what we're going to do in lab is we're going to do tests. This is going to be the identification of an unknown ionic compound lab that we do after the midterm. And the test is we're going to create an activity series for the halogens. Which one has the highest oxidizing strength? Which one has the weakest oxidizing strength? And it's going to be based on these tests. We're going to do something very similar here. And basically what happens is, so for these reactions in the lecture class, we will not be looking at the halogens. This right here, this is just lab only. And so for lab, we're actually not going to use the activity series. We're going to make our own activity series, which is kind of fun. So what happens is, just so this will help you with lab, is whatever element ends up as the anion, in this case, the fluorine, right? It is the element that is reduced, which makes it the better oxidizing agent. So if we're trying to figure out, activity, it's a little bit different. In this case, the fluorine has much greater oxidizing power than the iodine. All right, so fluorine, oxidizing power, fluorine is much stronger than the iodine. All right, so F stronger than I. Okay, so we're going to do a series of tests with the halogens. We can't use fluorine because it is just not good to use. We're going to use chlorine, bromine, and iodine, much more human friendly. But we will work in the fume hood because the halogens, if you're breathing them in for a while, like iodine has always been one of those ones that it can kind of trigger just a slight headache for me. But if we keep them in the fume hood, we don't have any issues. Okay, so might help you a little bit for the lab. Now, I wanted to do one more example about redox. When I talked about redox on Tuesday, I introduced, okay, what is oxidized? What is reduced? What does that mean? We talked about how it means that there's an exchange of electrons. For redox reactions that are not single displacement, you're going to be given the reactants and the products. Because if I just gave you I negative with nitrite, there'd be really, you'd be like, what? I don't know. This isn't double displacement. It's not combustion. It's not acid base. You might think single because there's a single here, but there's no activity series to look at. So with just kind of generic redox reactions that don't fit into one of the categories, like single displacement, technically combustion is redox as well, then we would have to, my computer froze real quick. We would have to be given the reactants and the products in order to figure out what's happening. All right, just bringing my video back. There we go. Okay, so we've got our reactants and products. So what would happen here is if I gave you this equation, I might ask you, okay, what is oxidized? What is reduced? Or what is the oxidizing agent and what is the reducing agent? In order for us to know that, we'd have to go and look at all of those oxidation states. And that was something we practiced on Tuesday. So if we look at the oxidation states, remember, this is kind of the same as a charge, but not exactly. If the element is by itself and there's a charge indicated, that is the ion charge. It is also the oxidation state. So iodide here on the reactant side has a charge or an oxidation state of -1. For the nitrite, right, what we said was when we're assigning oxidation states, always go with the perimeter of the table first. In other words, when I look at this, oxygen is closer to the end, the perimeter. So we're going to do oxygen first, and then nitrogen will be the unknown, the one that we don't know. So oxygen is -2, but there are two of those present, right? So two oxygens, each -2 means I've got a -4 total. The charge on the polyatomic ion is a -1. That means the nitrogen would have to be a +3. So +3, -2, -2, overall gets me to a -1. So those would be the two oxidation states of nitrogen and oxygen in nitrite. The iodine on the product side, I2, no charge indicated. That means the charge or the oxidation state would be 0. And let me just put that as I over here. And then the NO, this one a little bit easier. We know oxygen is a -2, so that means the nitrogen must be a +2. So when I look at the oxidation states, now I can figure out what has been oxidized, what has been reduced. So first, let's look at the oxygen. Oxygen has gone -2 and it stays -2. So oxygen is not part of the redox, except it's there because it's the right compound or the right polyatomic ion. But the charge on the oxygen doesn't change, so it's not part of the electron exchange. Instead, let's look at the iodine. Iodine has a -1 charge on the reactant side, and now it has a charge of 0 on the product side. What I notice is the charge is going from a -1 up to a 0. When it's increasing, that means it has been oxidized. And the reason for that is the charge has gone up because negative particles have been released. Okay, so oxidation, electrons have been lost. All right, then if I look at the nitrogen has gone from a +3 charge down to a +2 charge. Okay, so the nitrogen here is what's been reduced. It's gone from a 3 down to a 2. And that's because electrons have been gained. So if I gave you this particular equation and I said, okay, looking at this equation, determine all your oxidation states and then tell me what has been oxidized. Your answer would be, well, the I negative has been oxidized. And then if I asked you, okay, well, what's been reduced? Okay, Avery, I'll go right back over that in just a second. The N in the nitrite has been reduced. So the +3 in the nitrite, where this came from is let me change my color on the pen. Basically, we're going to say nitrogen is X. We don't know the charge on the nitrogen. Oxygen, we know there's -2, but because there's 2 oxygens, I got to multiply that by 2. And then I don't want to forget that there's a polyatomic ion charge here. And that means that the overall charge, it hasn't gone to 0, it's gone to a -1. So overall, I have a -1 charge. So if oxygen is -2 times 2, so -4, my overall charge is -1. What would nitrogen be to add to a -4 to get me to a -1? And that would mean that it had to be a 3. So nitrogen has to be a +3. So when you're looking at the oxidation states, every compound, right, or polyatomic ion, they're all separate. So just looking at the iodide, -1. Looking at the nitrite, just looking at that unit, trying to figure out the charge of nitrogen and oxygen. The I2, just separate as a unit, that's neutral. And then nitrogen monoxide, just looking at that. Oxygen's -2, so nitrogen must be +2. Okay, and then once you know your oxidation states, you can see nitrogen has been reduced, went from a 3 down to a 2. And the iodine has been oxidized. It went from a -1 up to a 0. So I know the mnemonics like oil rig or something that oxidizing means losing electrons. I just think sometimes students see the negative and they think lost, but remember negative means that you're gaining negative. What I always thought was way more literal and easier, I thought, just to keep it straight, is that whatever is reduced reduces its charge. That way you really don't have to think too hard. Just whatever's reduced reduces its charge, because there's a lot to think about on a test, you know that. So to go from a 3 down to a 2, that shows reduction. That means the other element that changed charge, in this case, the iodine, was oxidized, and it's because the charge went up, became more positive. All right. Now, remember the terminology. When something is oxidized, that means it is the reducing agent. And when something is reduced, it means it is the oxidizing agent. All right. Now, the other question that came in was, when we were doing the nitrite, how did we know to put oxygen as the -2? So when we were looking at oxidation states on Tuesday, what I had mentioned is if I thought about this the way we've learned it, like oxygen's -2, nitrogen's -3, this wouldn't make any sense. So you have to pick one of these 2 elements to have the charge that you know it is based on looking at the table. And then the other one will be the unknown. The unknown is the one that's going to be farther away from the perimeter. So like we know noble gases love to be 0. We know halogens love to be -1, oxygen family -2, nitrogen family -3. But when I look at this, one of these has to be the unknown, right? Because we're looking at the nitrite NO2. If I'm looking at one of these being the unknown, whichever one is closer to the edge of the table is the one that I want to stick with. So oxygen will be -2. The nitrogen will be the unknown. There are some exceptions. Really what this comes down to is electronegativity, which we haven't covered yet, because we don't get there until we start looking at trends in the periodic table. But technically, oxygen is our second most electronegative element. So the only possible charges are either 0 when it's by itself as oxygen gas, or -2 when it's part of anything else. Now, technically, there is peroxides and superoxides. There's always exceptions, but we're not going to worry about those. So oxygen, if it's part of a compound or polyatomic, is going to keep the -2. But nitrogen here would be the one that we don't know. That's what we have to try to figure out. And so that's why nitrogen was the X. That's the one we wanted to figure out. All righty. So that's the end of chapter 5. Now what we want to do is transition into chapter 6. So again, chapter 5, there's a lot of worksheets. There's a worksheet just on oxidation states that I think is really good practice, because most of this chapter, again, has been things that you've seen before. Like you've done double displacement in intro, you did single displacement in intro, we did solution stoichiometry, but redox and oxidation states you have not probably done before. I don't cover it in my intro chem lecture. So there is a worksheet just devoted to oxidation states. And that might be something to help you practice that if you just want to look at that particular topic. All right. And then just to make sure everybody knows, when it comes to the test, right, your solubility rules will be given and your activity series of metals will be given. So you do not have to memorize that. All right. So then what we're going to do is we're going to transition and take a look at chapter 6. If my computer will focus. Okay. I'm going to shut it off really quick and turn it back on. That'll give you time to get your chapter 6 notes if you don't already have them. Uh-oh. Oh, there we go. Okay. Chapter 6, another chapter filled with, I think, material that you probably remember from before. Gas laws, most everybody loves gas laws. We have formulas this time. That's always nice. You have something where you can just kind of plug and chug. So with gas laws, if you remember from intro, gases require a lot of information. In order for us to understand how much gas is actually in the sample, we would probably need to measure the volume of the sample. But remember, volume of gases is flexible. Unlike liquids and solids where it's fixed, we can squeeze a gas into a smaller volume, or we can open it up and let it expand, you know? So volume doesn't really give us the full picture. We also need to measure the temperature that we're at, because we know that at lower temperature, I always thought of it like gas molecules want to huddle together for warmth. So if they're at lower temperature, they take less volume. So temperature is another measurement we have to take. And then on top of it, we have to have pressure. And pressure is really a measurement of molecular collisions. The more collisions there are of the molecules in the sample, the higher the pressure will be. Now, volume units we're used to. We've been seeing milliliters, liters, cubic centimeters, et cetera. We could do cubic inches, cubic feet, right, if we're not on the metric system. But of course, we want to be on the metric system. So we're going to be either milliliters, liters, cubic centimeters, the same as a milliliter. Temperature, we know Celsius, Fahrenheit, Kelvin. As a chemist, I could argue there's no reason we should ever use Fahrenheit again. When we go into lab, we use Celsius or centigrade thermometers. But for gas laws, you always have to be in Kelvin. That is a restriction. We have to be on the scale where there is absolute zero. There's no negative. So we always have to be on the Kelvin scale. So if you get a measurement in Celsius, which a lot of times you will, especially if we're in lab, make sure that you remember to add the 273.15 to get it into Kelvin. And of course, we saw that on the first test. Pressures may be new. Pressure is not a unit that we've really talked about since intro, but the units that we have here are ATM, which is short for atmospheres. It's the standard unit, millimeters of mercury, and torr. And if you're wondering why there are two units that mean the same thing, meaning it's a 1-to-1 ratio, it's because torr is short for Torricelli, who was the scientist who invented our way of detecting atmospheric pressure. And it is a mercury column, open-ended, where the atmospheric pressure, if it rises, it pushes the mercury in the column up. And so the distance of the mercury in the column, or the height of the mercury, is actually how we can measure atmospheric pressure. Manometers and barometers are kind of cool. I mean, I always think it's so interesting how you think of that. Anyway, so that's why the millimeter of mercury and the torr are exactly the same. Seems a bit redundant. I don't disagree with that. But that's why there's two. Torr is short for Torricelli. He's the guy that invented the millimeter of mercury measurement. So those are exactly the same. I'll be honest, a lot of times I forget which one I'm using and I kind of interchange them. I hope not to do that because I don't mean to confuse you. But torr and millimeter of mercury, same unit. Just like a milliliter and a cc, cubic centimeter, the same unit, right? Atmosphere, though, is the standard. So we definitely want to be comfortable working in atmospheres because that is our standard unit for pressure. All right, so the couple of gas laws here. Boyle's law, and maybe I should, but I don't really care about the name of the scientist, so don't feel like you've got to memorize Boyle and Charles, and I don't need the name. But Boyle looked at pressure volume relationships, and everybody finds this relationship so intuitive that if I'm looking at a container of gas that has, I don't know, those moles of gas inside, if I open up the volume and I put that same sample of gas into a much bigger space, pressure has gone down. Because if we're going back to molecular collisions, well, now that the gas molecules have more space, they're going to collide less frequently. So what we're looking at here is if volume goes up, pressure goes down. Or the opposite is true. If I squeeze volume, now the gas molecules have less space, so pressure goes up because collisions have gone up. That indirect relationship, one goes down, the other goes up, is something we express this way, right? And that was like the dilution formula we had, M1V1 equals M2V2. As volume goes up, concentration goes down, same thing's happening here. So in this formula, pretty easy, plug and chug, your units are really not picky. You just have to have the same unit for volume on both sides and the same unit of pressure for both sides. So in other words, like if P1 is given to you in ATM and P2 is given in torr, you have to fix that first. Just make sure P1 and P2 units match and V1 and V2 units match, but otherwise it doesn't matter what unit you're in. So first example says, we've got a sample of helium gas at 535 milliliters, 988 torr, 25 degrees Celsius. The sample's transferred to a 1.05 liter flask, constant temperature, and we want to know what the new pressure will be. So first thing, if the temperature doesn't change, that means we can ignore it, right? The only time it would matter, right, is if the temperature changed. Then I would have to factor that into my equation. But if it's the same, if it's constant, then we don't have to worry about it. Then the other thing I need to think about, okay, is I've got 535 milliliters at 988 torr, volume's going to 1.05 liters, and we want to know what the new pressure will be. So what I always did with these is I was like, okay, this is my formula, pick my formula, P1V1 equals P2V2. And then I line everything up. And of course, you do not have to do this. I think it helps me be organized. Torr is our unit for pressure. So we're starting out at 988 torr. Our volume starting out 535 milliliters. We're looking for the new pressure when the volume goes to 1.05 liters. So this is what I was talking about. The unit doesn't matter as long as they match. So what I notice here is that V1 and V2 do not have the same unit. So this is where it's your choice. Do you want them both to be in milliliters? Do you want them both to be in liters? Doesn't matter. It's just they have to be the same unit. So if you want to take V1 to liters, divide by 1,000, go ahead and do that. Then you'd have 0.535 liters. If you wanted to go the other way and multiply it by 1,000 here, V2 would be 1,050 milliliters. Now the gas laws, the formulas, you do want to memorize these, but I'm going to show you that there's really only two formulas that you have to memorize. I think I mentioned this when we were talking about polyatomic ions. If I don't have to memorize something, that's better. Especially now, my memory is definitely not what it used to be. So I really don't like memorizing things. So you'll notice in gas laws, there's a lot of formulas, but you really can narrow it down to just two. And that's what I'm going to present. Just memorize these two formulas, and then you've got the whole chapter. Okay, so I've got P1, V1, V2. P2 is the unknown, or the X. We took V1 to liters just because V2 was in liters, but again, they both could have been in milliliters. That part doesn't matter. Now we can plug and chug. We're solving for P2. So I'm going to go ahead and divide both sides by V2 so that I can get rid of it on the right. Now I can plug everything in. So my P1, 988 torr, my V1, 0.535 liters, and then my V2, 1.05 liters. The other thing I like about gas laws is if I can kind of think about what I expect should happen to the answer, I like that. It gives me a little bit of security. In other words, volume is going up, went from like half a liter to a liter. So that was this example here. If volume's going to be going up, pressure should be going down. So let's calculate. We got 988 times 0.535, divide that by 1.05. We're going to keep three sig figs. Everything's got three. Answer I get here is 503. And the unit that I'm left with is the same unit as P1, which is torr. Pressure went down because volume went up. So that looks like it makes good sense. All right, so nice and easy. P1 V1 equals P2 V2. That's Boyle's law. Here's another one. It says we got a sample of air this time. We're at 73.3 milliliters, 98.7 kilopascals, and 0 degrees Celsius. And we want to know what happens if the pressure goes to 4.02 ATM. What would the new volume be? And again, it gives you a temperature, but then it tells you that the temperature doesn't change. So again, that means we're going to ignore that temperature because it doesn't factor in. It won't change the pressure of the volume because it's constant. Temperature's constant. All right, so another Boyle's law problem. We got P1, V1, P2, V2. All right, and then if I look at everything, initial pressure, 98.7 kilopascals, volume, 73.3 milliliters, P2, 4.02 atmospheres, V2, unknown. That'll be our X. All right, so same problem we had with the last example. That is, in this case, the pressure units don't match. So I gave you the conversion. This is not one you need to memorize. Let me go back up to the beginning. I do want you to memorize the conversion of ATM to torr to millimeter of mercury. This is just a really important one to have memorized. So just remember those two units are the same, just like milliliter and cubic centimeter. And then 1 ATM is 760 torr or 760 millimeters of mercury. If it's a Boyle's law problem, question just came in the chat. If it's Boyle's law, temperature must be constant. It's not factored into the formula. So if it's a Boyle's law problem, the temperature will be constant. So notice in both of these examples, the temperature is not changing. All right, before I can plug and chug, I need to get either both units into kilopascals, yes, or I need to get both into ATM. And again, doesn't matter which way you prefer to do it. Just because ATM is the standard unit, I'm just going to pick that one, but it wouldn't matter. You can use either way. So I'm going to, using that conversion factor that's given to me, kilopascals on the bottom, 101.3 kilopascals is equal to 1 ATM. So when I calculate P1, I'll take 98.7 divided by 101.3, keeping 3 sig figs, I get 0.974 ATM. Okay, sorry for kind of squeezing that in. All right, so I've got my P1 and ATM to match my P2 and ATM. Got my volume in liter or milliliters. I can just keep it in that. So in this one, for my P1 V1 equals P2 V2, I want to solve for V2. So I'm going to divide both sides by P2. That's going to get rid of that over there. Now I can plug in initial pressure in atmospheres, 0.974, volume, 73.3 milliliters. All right, and then my P2, 4.02 ATM, and that'll get me to V2. So I'm going to look at this really quick. Pressure's going up by a factor of 4, so volume should be going down by a factor of 4, roughly. So 0.974 times 73.3 divided by 4.02, I get 17.8 with 3 significant figures. And the unit, ATM's canceled out. We got a unit of milliliters left. So that's our volume. So in this example, pressure went up, so volume went down. All right, so that's Boyle's law. Boyle's law, again, doesn't really matter to me if I don't need you to know Boyle, right? Let's face it, he's dead. So we don't need to know his name. But I just need you to know the relationship, the formula. And indirect relationships are just always given this way, right? The product of the two variables is equal to the product of the two variables after the change. So P1 V1 equals P2 V2. All right, so the formula I need you to know, but not the name. So Charles' law, Charles, again, don't need to know Charles, but he was another scientist, except he looked at volume and temperature. And now in this case, pressure will be constant. So instead of temperature, pressure is not going to change here. We're going to keep pressure the same, which means we're going to keep collisions the same. So what'll happen here is, and a lot of students know this, I think, intuitively as well. If you heat a gas, right, gases like to expand. If we're going to keep the collisions the same, right, because pressure is the same, if I heat a gas, they start to move with greater velocity, kinetic energy, and so those collisions are going to happen more frequently. What would I do to volume to make the collisions come back down to where they were, to hold pressure constant? Well, I'm going to have to expand the volume. But a lot of students know this, that if you heat a gas, it wants to expand. If you cool a gas, it wants to condense. It wants to shrink. So that's a different relationship, right? If you increase temperature and you increase volume, that's now direct. If one goes up, the other goes up. That's a direct relationship. So that formula is different. It's V1 over T1 equals V2 over T2. So that's Charles' law. So for this one, the volume unit you pick doesn't matter as long as V1 and V2 have the same unit. Again, it can be both milliliters, both liters, both cubic inches if you want. But this is where it starts to become important to always remember temperature always has to be in Kelvin. And I'll say it a lot, and inevitably there will be a couple students that will just forget that and they'll leave it in Celsius, but make sure you're always on the Kelvin scale. All right, so remember that conversion from the first chapter, the temperature, you add your 273.15 to get to Kelvin. If you do see a problem with Fahrenheit, right, make sure that you subtract 32 first, then divide by 1.8 to get you to Celsius, and then convert it to Kelvin. But again, this is another formula that you got to memorize. All right, so V1 over T1, I don't need two equal signs, sorry, equals V2 over T2. So another formula, but again, I'm going to show you how you really only have to memorize two formulas. All right, so example here, we have a sample of hydrogen. It's got a volume of 692 liters at 602 degrees Celsius. Pressure is constant. Okay, so again, that means don't worry about it. And we want to know what would the volume be if we cool it down to 23 degrees Celsius. So again, kind of intuitively, what do we expect? Temperature is dropping quite a bit, so volume should also be dropping quite a bit. But we can pick, we see that we've got V1 over T1, V2 over T2, right? We're looking at volume temperature relationships. So this is, again, you don't need to know Charles, but that's the correct formula. And then if I line everything up, my initial volume is 692 liters. Initial temperature is 602 degrees Celsius. All right, but again, make sure you always go to Kelvin. So we're going to add that 273.15, but we're going to keep the decimal place, right? So 602 plus 273.15, we'd go to 875 on the Kelvin scale. Then for T2, we have 23 degrees Celsius. When I add 273.15, we're going to keep that at 296 Kelvin. Okay, so remember when you do your temperature conversions, the original temperature, the decimal place, that's what we want to keep when we do the conversion. So 23 degrees Celsius looks like it's only 2 sig figs, but once we convert it to Kelvin, it's actually 3 because we kept the same decimal place. All right, so now we have all of our inputs. We're going to solve for V2. So that means when I look at my formula, I'm going to multiply T2 on both sides. So we're going to cancel out T2 on the right. Now I can plug in my T2 after converting to Kelvin was 296. My V1, 692 liters. And then if I divide that by my T1, 875 Kelvin. Now, if you plug and chug in the calculator and you notice like your V2 is higher than your V1, then you know you got the temperatures backwards. Like we know since the temperature is cooling down so significantly, even at all, even if it's a minor amount, since temperature is dropping, volume should be dropping. So if you somehow got your temperatures flipped and you ended up with a volume that's increased, you'd know something went wrong, right? So temperature dropping, volume should be dropping. So we're going to take 296, multiply it by the volume of 692, and then we're going to divide that by that temperature in Kelvin of 875. And what I get here is 234. And then, of course, the question is, what's the unit? Kelvin cancels out, so we're left with liters, and that would be my volume. And just like we expected, temperature dropped, so volume dropped. All right, a direct relationship for Charles' law. All right, one more example here. We got a 575 milliliter sample of carbon dioxide gas. We're at 602 degrees Celsius again. What temperature should the CO2 be heated to occupy a volume of 22.4 liters? So in this one, it doesn't say anything about constant pressure, but because pressure is not mentioned, we're going to assume that the pressure is constant. So anytime there's a variable pressure, volume, or temperature that is not mentioned in the question, then we assume it didn't change. If it did change, it would have to be reported. So we don't have to worry about pressure here. So again, this is going to be V1 over T1 equals V2 over T2. So plug in everything in, or at least lining everything up. Initial volume, 575 milliliters. Initial temperature, 602 Celsius, but like we saw earlier, when we convert that to Kelvin, that's 875 Kelvin. Then my V2 is the unknown. Oh, no, sorry. My V2 is 22.4 liters. My T2 is the unknown. All right, so before I can plug and chug, I need to either be both in milliliters or both in liters. So I'm going to go ahead and go to liters. I'm going to divide by 1,000 for V1, and I get 0.575 liters. All right, now this one, algebraically, just slightly more complicated because we're solving for T2. Inevitably, what some students will do is they'll say, okay, I'm solving for T2, so I'm going to divide both sides by V2, right? So they put V2 on the bottom on both sides. It cancels out over on the right. And they say, okay, there, I'm done. The problem, though, is at this point, what you have is the inverse of T2, right? We got rid of volume in the numerator, but T2 is still in the denominator. So at this point, this is why I loved math. It's just so easy. Like the logic of it, I love it. So it's kind of perfect. All we have to do is, because we want T2 in the numerator, all we have to do is just flip the equation. So anything on the bottom goes to the top, anything on the top goes to the bottom. So I'm going to cover what we just crossed out in the middle. So on the right side, instead of 1 over T2, we're going to change that to T2, because T2 will move to the numerator and the 1 would go to the denominator. We're going to do the same thing over on the left. So the T2 would be equal to, on the bottom, V2 goes to the top, T1 on the bottom goes to the top, and then the V1 on top goes to the bottom. All right, so that's one way to do it. The other way to do it, and I like that way, but if you like this way, V1 over T1 equals V2 over T2, is since we're solving for T2, what I was, remembered was anything that crosses the equal sign does it diagonally. So to get T2 by itself in the numerator, we're going to move it over here, which means we need to move T1 over here and V1 over there. So what we end up with is T2 on the top, V1 didn't move, T1 cross multiply to the top numerator on the right side, and V1 dividing both sides. So now the denominator on the right side. We end up at the same place. So you pick whichever one you like better, whether you just want to flip the formula and solve for T2 or just make sure everything goes diagonally. But we get the same formula either way. This is another one because the algebra might be a little bit harder. What do we expect, right? What we see here is that the volume is going way up, right? Which means temperature should be going way up. So let's see exactly what happens. So we get a V2 of 22.4 liters, the initial temperature of 875 Kelvin, V1 0.575 liters. That'll get us to T2. So again, volume went from half a liter to over 22, so went way up. So what should be happening to temperature? It should be going way up. 22.4 times 875 divided by 0.575. And in fact, we get a very large number, 34,086.956. But if we're thinking about significant figures, we should only have 3. So we would go 1, 2, 3. So it would be 34,100 Kelvin. Okay. All right. So that would be our temperature that we would have to heat the CO2 up to in order to get that huge increase in volume. All right. So for Charles' law, we're looking at volume and temperature relationships. For Boyle's law, we were looking at pressure and volume relationships. Again, I mentioned, not important to me if you remember Boyle and Charles, the name. So instead, as I mentioned, I like everything to be simplified to just 2 formulas so that you can answer everything in gas laws with one of these 2 formulas. So what we're going to first look at is called the combined gas law formula. What we do is we take Boyle's law, we take Charles' law, we combine them. So on the next page, we've got Boyle's law, P1V1 equals P2V2. Then we've got Charles' law, V1 over T1 equals V2 over T2. When we combine them together, we've got the combined gas law. So what I like about this is one of our 2 formulas to memorize. So to me, this is really where you want to start memorizing, is on this page. All right, so I'm going to highlight. So we've got P1V1 equals P2V2. Now, if I think about the examples we've done so far, if I approached that very first page of notes and I thought, okay, well, if I'm going to use the combined gas law formula, what I look at here is if anything is constant, that means it would cancel out, right? If T1 and T2 don't change, it's a constant temperature, then mathematically it would make no difference. So we just cancel it out. If we were doing this last example where pressure's not mentioned, so we assume it's constant, then again, we would just cancel it out. So with the combined gas law formula, what the first thing we're going to note is, right, is if any variable is constant, then that just means it cancels out. All right, it'll cancel out. So that's the first thing. So if anything's constant, then we just get rid of it from the equation. The other thing is, if we're trying to narrow all of gas laws down to 2 formulas, then it would be really helpful to have it very clear when to use which formula. So what we do is the P1V1 formula, the combined gas law. This is our formula for change. So if there's any kind of change in conditions, if the gas is heated, if the volume is squeezed, if the pressure goes down, right? This is our formula. Avogadro's law is really going to come in more for me with the ideal gas law. Technically, the mole volume relationship is there as well, but I don't tend to ask too many questions using Avogadro's law unless it's going to be stoichiometry, in which case we're going to use Pivnert instead. So that question came into the chat. Yes, there is Avogadro's law, but I like to deal with Avogadro more when we do ideal gas law. So I'll talk more about that in a little bit. So we're going to look at this combined gas law. P1V1 equals, or P1V1 over T1 equals P2V2 over T2, right? So again, if any one of those variables is constant, it just cancels out. This is the formula we pick if there's any kind of change in conditions. If the gas is heated, volume is changed, right? This is going to allow us to look, okay, what happened before it was heated? What does it look like after it was heated? And on this one, the only unit that's picky is temperature must be in Kelvin. All right. Other than that, pressure doesn't matter as long as it's the same on both sides. Volume doesn't matter as long as it's the same on both sides. But temperature has to be in Kelvin. Temperature is the one that matters. The other formula is about halfway down the page. So I'm going to come back to that example in just a second. This is the ideal gas law. This is the question that came up, and that is PV equals nRT. Notice there's no change here. There's one pressure, one volume, one temperature. So nothing could be heated here and then let us figure out pressure. You know what I mean? Like this is just everything's constant. This is looking at the gas just at one set of conditions. All right, so that's the first thing is this is our formula when there's no change in conditions. Right? There's only one pressure, one temperature, one volume. The other thing that's different here that we haven't seen in a Gasol formula yet is that we have N. And N is moles. Oops. N is the moles of gas. So this is going to be our formula if we're going to do any kind of stoichiometry. So if we're going to go through the mole ratio and compare moles of A with moles of B, and we're going to look at stoichiometry, then we're going to go obviously through the mole ratio. So this is our formula to use for any kind of stoichiometry because it has moles in it. And as I mentioned when we first started this chapter, in order to really understand how many moles or molecules are in the sample, the volume doesn't tell us enough. We also need to know the pressure and the temperature to fully understand how many particles are there. The pressure tells us how many collisions. The volume, right, tells us how many collisions there's, we would think there would be like less volume, more collisions, right? Higher volume means less collisions. Temperature also, how many collisions, because how fast are they moving? So we need a lot of information when it comes to gases to really understand how many particles are in the sample. Then the question is, okay, well, how do you relate pressure, volume, moles, and temperature? And you do that through what's called the ideal gas constant, which is R. And it is 0.08206 liter atmosphere per mole Kelvin. All right. And I do want you to memorize this. It's the conversion that we do. You'll have it memorized whether you like it or not, because you just use it so often. Now you can look up different R constants, but I don't want to do that. We're just going to use this one, but just know that if you use this R constant, your units start to look very specific. If you use the 0.08206, what that means is your volume would have to be in liters, right? Back up here, P1V1 equals P2V2, we could have both been in milliliters. That didn't matter. But now it matters. Volume has to be in liters. Pressure has to be in ATM. Can't be in torr or millimeters of mercury. And then, of course, what is the same? Temperature has to be in Kelvin. And that's always true, no matter what formula you use. All right. So now that I'm kind of narrowing it down, I'm going to say every time you read a gas loss problem, I want you to think, first question, do I use PivNert or do I use P1V1 over T1, right? Which formula is the right one? So now let's go back and do that example we just skipped over. It says we got an aerosol container. It's filled with a gas at 2.5 atmospheres and 22 degrees Celsius. If it's possible that the container could rupture if the pressure goes above 8 ATM, what temperature is that likely to happen? So what's happening here is we've got this aerosol container with a volume, right? We're looking at just that temperature right before it ruptures, meaning the volume's going to be staying constant until I get to that rupture. So volume is constant. So that's the first thing I look at. Now, the second thing is what formula? What I can see is I've got a starting pressure and a final pressure, right? I've got a change in conditions. I've got a starting temperature and I want a new temperature. Again, I've got a change in conditions. So if I'm asking myself which formula, it's got to be the P1V1 over T1 formula, right? This allows me to plug in both pressures, looking at the change in temperature. PivNert wouldn't allow me to do that. So I'm going to be using P1V1 over T1 equals P2V2 over T2. Now, because volume is constant, right? We're assuming we're going right to rupture. So we're keeping volume of that aerosol container constant. That means that V1 and V2 are going to cancel out. because it doesn't matter. If it was a 1 liter container, it would be 1 liter for both. If it was 5 liters for both, right? So the volume of the container isn't what's changing here. It's just the temperature and the pressure. So I've got my formula adjusted now because volume is constant. Okay, so again, because it was constant, we're going to cancel it out. All right, now let's move the formula around because like we did before, we need to solve for T2, which is on the bottom, right? We want to know the new temperature. So depending on what algebra you like better, if I divide both sides by P2, we cancel it out on the right side, but then I'm going to need to flip it. So what I end up with here is P2 times T1 divided by P1 equals T2. So T2 moves to the numerator, P2, T1 move to the numerator, P1 moves to the denominator. So now we've got our adjusted combined gas law formula. All right, so now I can plug in. P2 was 8.0 atmospheres. That was the pressure we were going to. The T1, we started out at 22 degrees Celsius, but remember, we've got to take 22 and add 273.15 to make sure we're in Kelvin. All right, and then the P1 in the denominator would be that original pressure of 2.5 atmospheres. So we have 8.0 atmospheres times 295 Kelvin, keeping that the ones place, the decimal place, dividing that by 2.5 atmospheres. Okay, so I'm going to take 8.0 times 295, divide by 2.5, and I get 944 Kelvin for my T2. All right, so basically, if I take that aerosol container and heat it up to about 944 Kelvin, that's when it's going to rupture. Now, real quick, if we look at our sig figs, both pressures only have 2, so my answer should only have 2. So I'm actually going to round that to 940 just to keep the 2 sig figs. So that would be the temperature that I could heat that aerosol container to before it ruptured. Anything more than that and rupture would be likely to occur. All right, so let's try another one. But in this one, again, all the problems from here on out, I want you to ask, and I do mean that, all the problems from here on out for the rest of chapter 6. I want you to start with, is it a P1V1 over T1 question, or is it a Pivnert question, right? And that's actually, we're right at the end of the first part. So this is a good place for me to stop. So I'll meet you back in the next session at 12:30, and we'll pick up right where we left off with more examples. So I'll see you in just a little bit. We got like a 10-minute break.